Good morning, math peeps. Hope you're all doing well. Today's lesson is called Implicit Differentiation, and you'll see that when you use implicit differentiation, you basically use it when you have both x's and y's in your equations. You'll see what I mean in a second. So, let's just do this derivative like normal. Okay, we don't have x's and y's mixed together. So if I just said from the start, find this derivative, then dy dx equals negative 15x squared plus 4x. No big deal. But if you look back, really what we've been doing this whole time, we're doing the derivative of both sides of this equation. The derivative on the right side is what you're focusing on, but the derivative on the left side is also true, meaning the derivative of y with respect to x is dy dx. Now is the time when we're really going to focus on what does dy dx mean, okay? dy dx. This denominator here tells you that that is the variable you are actually allowed to differentiate, okay? We're only allowed to differentiate the x's. So when I differentiate a y, the derivative of y is 1 dy dx. What does that mean? Well, let me just show you. Basically, here's what's going to happen. When you take the derivative of anything that has an x, you'll do the derivative like normal. But if you take the derivative of anything with a y, you'll tack on a dy dx at the end. So, for example, if I had 3x squared minus 5y to the third and a bunch of other junk, okay? If I do the derivative with respect to x, then I treat the x's like normal. But when I do the derivative of the y, negative 15y squared dy dx. Every time you do the derivative of a y term, you're tacking on a dy dx. What you're really doing is a chain rule, because the derivative of y is dy dx. So when I did the derivative of this, the derivative of the outside was 15y squared times the derivative of y dy dx. The short of it's going to just be when you do the derivative of a y, you're going to add a dy dx every time. And it actually is very easy once you get used to it. Okay, so here we go. All right, this problem. I could get y by itself and then do the derivative like normal, but I would only be able to do the top half and the bottom half of this circle separately. So here's how you would do it using implicit differentiation. Okay, the derivative of x squared, I do normal, 2x. The derivative of y squared is 2y dy dx. Bring down my equal sign, and the derivative of a constant is 0. Now, in order to find the derivative rule, you just got to get the dy dx by itself, just like a regular variable. So I'm going to subtract 2x on both sides, which gives me a negative 2x. Get the dy dx by itself, so divide by 2y. And I get dy dx equals, the 2's cancel, and we get negative x over y. Now, what does that tell me? This derivative equation still tells me the same thing it used to tell me. It's going to tell me the slope of this curve anywhere along the curve. But it's still waiting for me to tell it where do I want that slope calculated. So, for example, if I plugged in the coordinates right here, what is the slope right there? Well, hopefully you can see that has a 0 slope. And that is because the coordinates there are 0, 1. So if I plug in 0 and 1 for my coordinates, I get a slope of 0. Well, how about right here? That slope looks like it's vertical. Well, that's because the coordinates there would be 1, 0. So if I plug that into my slope equation, we'd get a negative 1 over 0, which is undefined, and that's why we have a vertical slope right there. Okay? Even if I plugged in the point right here, you might know from your unit circle that the coordinates right there are square root of 2 over 2 and square root of 2 over 2. Well, if I plugged that into my derivative equation, you'd get the same number over itself with a negative in front. That would give me a slope of negative 1. And that's why the slope right here is exactly negative 1. So, implicit differentiation. You use it when you have x's and y's mixed together. usually you have to use it if you can't isolate the y. This one we could have done the old way if we got y by itself. So when you do the derivative of an x term, you do it like normal. When I do the derivative of a y term, I tack on a dy dx. And then I have to algebraically get the dy dx by itself in order to get the derivative equation. And it often has both x's and y's in it. So when you try to evaluate it, you need to know both the x and the y coordinate. All right, so that's the basic gist of it. That was an easy problem. The only thing that's going to change from here is just the mechanics, the computation, and that kind of thing, simplifying. All right, so give it a shot. Remember, every time you do the derivative of a y, you tack on a dy dx. So the derivative of 2y would be 2 dy dx. Bring down my equals. Derivative of x squared is 2x. Derivative of sine y is cosine y, dy dx. Don't forget that dy dx. Now that dy dx is like a 5 or a 2. It could go out in front of the cosine, but it's not really attached to this y. All right, now, how do you isolate the dy dx when you've got two of them? Okay, the same way if you had x's on two sides of an equation. You just get them both together on the same side. Okay, so I want this term, this is all one term, I want all of that to go over here where the other dy dx is. So I'm going to subtract it, that's all. Just do the opposite of this guy. So I'm going to leave this where it is, 2 dy dx. Subtract this whole big bunch of junk, minus cosine y dy dx. And I still have the 2x on the right side. Now my goal is to get dy dx by itself. How do I get dy dx by itself when there's two of them? Factor it out. Factor out a dy dx, and you're left with 2 minus cosine y. And now you can get dy dx by itself by dividing by 2 minus cosine y on both sides. And that's it. There's your answer. I can write it again nice and neat, but dy dx equals 2x over 2 minus cosine y. Okay? So get the dy dx's on the same side of the equation and factor them out. That's the main idea, but again, the computation gets a little trickier. This one is always a AP question. Just be careful with this one. The derivative of x squared is normal. Oops, hold on. The derivative of x squared is going to be like normal. The derivative of y squared, you're going to have a 2y dy dx. This guy is the troublemaker. How would you do the derivative of that? Well, that's going to be a product rule. When you do your product rule, though, make sure you keep the negative with the x. So I would put the negative x as one factor, the y as another factor. Do your two derivatives and crisscross, okay? Hit pause and give that a shot. Let's see how it goes. Okay, so the derivative of x squared is 2x. The derivative of the y squared is 2y dy dx. The derivative of 7 is 0. Don't forget that guy on the right. Now, the derivative of this guy. I have a negative x and a y. The derivative of negative x is negative 1. The derivative of y is 1 dy dx. Crisscross, okay? And I have a negative x dy dx minus y, and then attaching that was a positive 2y dy dx. Okay, hopefully you got that right. Now we just need to get the dy dx terms on the same side all by themselves, and anything that doesn't have a dy dx goes to the other side. So I'm going to leave my negative x dy dx on the left, leave my 2y dy dx on the left, move the other stuff to the right, negative 2x and a positive y. Okay, get the dy dx by itself, factor out the dy dx. We get negative x plus 2y, and then divide. Divide by everything attached there. Negative x plus 2y. Negative x plus 2y. So dy dx equals all of this. Now, you may have noticed I sort of jumped ahead here, but I didn't even read the directions. It said, find the equation of the tangent. Okay, equation of a tangent, you need two things, point and slope, point and slope. They gave us the point, the derivative is the slope, so now I need to evaluate this derivative. Okay, so here's my derivative. I have point, I need slope. So now here's how you write that, by the way. The derivative evaluated at, that's a little bar that tells you evaluated at the point -1, 2. Okay? Just plug in that all my x's are -1 and all my y's are 2 and evaluate that. Okay? So -2 times -1 would be 2 plus 2 all over 1 plus 4. So I get 4/5, and that's my slope. So my point is -1, 2. My slope is 4/5. Point slope form. Y minus y1 equals m times x minus x1. Done. See? Not so bad. Kind of fun. I like it. Moving on. Okay, one more. This one, you just might look at it and be completely confused because it looks tricky, but it's really not that bad. You've already done this stuff. And I didn't give you an equation, so you don't have to get the dy dx by itself or anything. I just want to know that you would know what to do with this if this was in the middle of a problem, okay? So if you're doing the derivative of 3e to the 2x, you know that. It's 3e to the 2x times the derivative of 2x, so times 2. Well, whenever you get something like this where you don't know what to do with it, always refer to an easier problem and get your mind straight. So for this one, the derivative of that would be 3e to the xy times the derivative of xy. Okay? And then the derivative of xy, that's going to require a product rule. And then you're going to put that in parentheses when you get that answer. Okay? So the derivative of xy, product rule, derivative of x is 1, derivative of y is dy dx. Crisscross, and here's my answer. 3e to the xy times x dy dx plus y. And then, depending on the problem, you may have to distribute and do some other stuff with it. All right, good luck, guys. I have one more. I want you to try this one on your own. Okay, last one. And this one doesn't have an equation, so I'm just saying what would you do with this if it was in the middle of a problem? Okay, so the derivative of the first term, same old, negative sine of 3x times the derivative of the inside. Okay, well this is the same thing, but there's a y there. So the derivative of the outside would be positive 3 cosine of 5y times the derivative of 5y. Well, the derivative of 5y is 5 dy dx. Okay, I put the 5 out front, which would turn that into a 15, but you still have to remember that dy dx because there was a y there. Okay, so this wouldn't be the whole problem. This would be in the middle of a problem, but I wanted to make sure you knew what to do if there was a y inside of a trig function or something like that. You still have a dy dx, and it might even be safer to put the dy dx up here. Doesn't really matter as long as you know the cosine 5y is one factor. The dy dx is a separate factor from that. All right, hopefully that's pretty easy. Hopefully I took it easy on you today. Good luck. Here's your homework. See you next time.